Hello everyone, this is HM Golam Samdani from Osaka University. Here I am going to give a presentation on an example application for seismic retrofitting of flat plate structure. So here mainly I will show how to strengthen the existing building, existing flat plate structure for retrofitting. My presentation is freezing.
Yes, it is not. Yes, it is not moving. Please share once again.
You not freeze. You can use the cursor on the keyboard maybe to move next slide, I guess.
Yes,
Okay.
now moves.
Now it's working. Sorry for this inconvenience. So firstly, I am showing the flow of seismic evaluation according to PWD manual, which mainly included the normal moment resisting frame structures. However, I'm not briefly describing about that. So, but in the case of this manual, flat plate structure were out of scope. In Bangladesh, flat plate structures is available, this like this, and interior columns were not connected with beams like that. So as a result, it's necessary to include the flat plate structure in our latest seismic SATREPS-TSUIB evaluation guideline. And as a result, we propose for a seismic evaluation of flat plate structures with a slight modification of calculating C index and F index. And that was the background. And I'm moving to my objectives. So my main objective is to show of this in this presentation to show a strategical plan of the seismic retrofitting, considering an example of application using typical flat plate building. So from Bangladesh, we collected an example building. However, some of the data are missing, and also some of lots of things we need to assume to show a simple retrofitting procedure. And it was a typical flat plate structure where the beams were exist in the exterior side, and no earthquake resisting designs were performed. From the outline of the building was a residential 6-story private building which constructed in 2015. And we did not get the soil data. That's why we are conservatively assuming it's a SD for Dhaka. From the summer materials, the concrete strength was around 24 MPa for column and 20 MPa for slab. For river yield stress, it was 400 MPa, and type of river was deformed river. So this is the typical floor layout of a flat plate building. Here you can see the structure exterior beams exist in the periphery frame, and the interior columns are not connected with beams. And the slab thickness was around 200 millimeter and 12 millimeter at 100 millimeter spacing, center to center top bars were used, and for bottom bar 200 millimeter spacing were used in that building. And total 4 different types of column schedules were used in this sample building. And here just I am showing the layout, but you can see that the layout is defined in for first floor this type, and for second floor to third floor this type, and fourth floor to onwards is this type. So mainly they are changing their column dimension and with the river diameter, and mainly the dimension of column and river area. So now I am showing the flow chart of seismic evaluation and strengthening. So mainly after collecting the building, we need to evaluate the seismic performance of the existing flat plate structures, which mainly we already proposed and presented in the guideline in April this year in WGT seminar. So by considering this, if the structure is the seismic capacity is greater than seismic demand, in that case the structure can be used continuously. So what's happened in our example building? Now, actually, I evaluated the building and calculated for all story and in both X and Y direction. And here I am showing on the C, the difference between C and F. So from here you can see that the X direction, only this green color that means sixth floor is fulfill the requirement of seismic demand in X direction. However, for Y direction, no story is allowing the seismic demand. So that means we are seeing the low seismic performance. More clearly, I am comparing the flow level with the seismic demand with the corresponding of seismic IS index. So here, this is the for X direction and this is for Y direction, and this is the seismic demand. So here you can easily understand that the very low seismic performance of the existing building. That means seismic strengthening is required. So I'm moving to the flow chart, and since the structure has a less performance, as a result, we need to move as per the following flow chart, which in my previous presentation, Professor Takahashi already described, so I'm skipping that. So after thinking about the retrofit, so what type of retrofit we can do for this sample building? So we need to think about that. And for the existing building, I am planning to use, first of all, post-install drop panel as a first trial. So here, this is the existing building, and drop panel were planned to install in the interior columns in here. And for sample calculation, I'm showing in X direction. And for X direction, you can see that only these columns will be contributed for the column shear resistance, because there's a connected in beam in corresponding respective direction. And after installing, so we are using the drop panel, and the dimension of drop panel is according to assumed according to the ACI BNBC code, and thickness and river also were used as per ACI BNBC code, but it's within and same as the original building. So before retrofitting, we found total 4 types of failure mode for interior column, and it was found that the punching shear failure is mainly dominated. So slab punching will occur. So after retrofitting using drop panel, what's happened? So it seems that the failure mode is changing to slab punching to slab yielding. As a result, we can say the shear max is no longer bound for 1/50. That means the upper limit of deformation angle can be removed, which may mainly affect the ductility index of the exterior columns. So before retrofitting, the exterior column, it was 2.6, the ductility index. After retrofitting, it's moving to 3.1. And here I'm briefly showing the first floor in X directional for all column cases. So total 12 columns were used, and here the C index and F index are showing. So this is actually the same as the existing building. So after retrofitting, the ductility index is improving 2.6 to 3.1, which increasing the seismic capacity. Where the C index were calculated according to this equation, the QU is the column shear resistance, and summation of W is the weight supported by the story constant. C index of columns connected without beam is ignored. So that's what I previously described. So exterior columns without beam is ignoring their shear resistance, C2 and C11. And for interior columns also, I ignored the shear resistance. And the ductility index F were calculated by the follow same as the PWD manuals. And finally, I can calculate the basic seismic index, which is the product of strength index C and ductility index F. And their relationship are showing here, and you can see the structure is meeting the seismic demand in this portion. So finally, we can find the seismic IS index, which is showing the 0.361, slightly higher than 0.36. So we can say that it is safe in first floor X direction. So as same manner, we can calculate the full structure in both directions. So here I am showing the C index and F index after calculating. So from in both direction, and you can see that the structure is safe. Some of the story is safe in X direction, and for Y direction, only one story is safe. More clearly, I am showing from the IS index. So this is for X direction, and this is for Y direction, and this is the seismic demand. So using post-install drop panel, so only the 6th floor in both direction is safe. However, for X direction, though, is safe, but not in all perspective. As a result, the conclusion from this strengthening of drop panel, only 6th floor is safe in both direction. Drop panel plan to install on the 6th floor. As a result, for 1st to 5th floor level, we need to use the more seismic strengthening technique. So strength-oriented retrofitting technique is recommended. Thereafter, post-install wing walls were used up to 5th floor level. And this is the original layout. And after using the wing walls, the layout can be like that. So where we use the wing wall dimension 500 millimeter for interior columns, and for X direction exterior columns, we use the wing walls 500 millimeter, and for in Y direction exterior columns, we use the wing walls 600 millimeter. And the sample calculation for Y direction, only these columns will be contributed for seismic shear resistance. However, wing walls with beam same as PWD manual, but wing wall without beam, that means interior columns, will be same as section 6.2, which are earlier described by Professor Takahashi. So why we are using post-install wing wall? So wing wall is a small wall panels which may not be considered as shear walls. So if the main advantages is it increases the lateral resistance of the column. For our case, the dimension of the wing wall can be like that, and where the dimension and detailing was assumed as per the Japanese guideline. From the original column, the interior column is like that, and the critical section was divided to distance from the column S. So when we are applying this type of wing wall, it extending their critical section. By preventing the critical section, by extending the critical section, is preventing the punctured shear failure. And the lateral resistance can be evaluated by this equation according to section 6.2. And now I am showing the first floor in Y direction overall result. So here you can see that the as same as the drop panel, I am showing the full table. But here we accounted the interior columns without beam, because we proposed in section 3.2 we can use in without beam, we can use the column with wing walls. And the C index and F index can be done by according to PWD manuals. And finally, we can judge the seismic IS index, and like for C index and F index for first floor is showing here, and the IS index showing the value is 0.375, which means it's safe. So what's happened for both direction in for all story. So here I am showing the all result of C index and F index, and you can see that the in both direction it fulfilled the requirement of seismic demand. More clearly, I am showing from the here. This is for X direction, this is for Y direction, and this is the seismic demand. So it increasing because we use the post-install wing walls, which effectively increasing the shear resistance of the existing column. However, drop panel was originally planned to be installed on the 5th floor only. So this is for drop panel, and up to 5th floor level we use the wing walls. So this part mainly. So wing walls were used up to 5th floor, and drop panel was used in 6th floor level, and the building is considered to be safe. From here you can see easily. Conclusion remarks. Simple retrofitting strategy was illustrated utilizing the proposed SATREPS-TSUIB guidelines. 6-story flat plate structure was retrofitted to satisfy the seismic demand. Existing structure has very low seismic performance in both directions. Seismic retrofitting was performed with a combination of wing wall and drop panel. Drop panel satisfied the seismic demand on the 6th floor level, but and wing wall satisfied the 1st floor to 5th floor level. So thank you very much for your kind attention.